The range power shift used in the case over 100 horsepower tractors is a combination of the 3-speed planetary power shift and a 4-speed mechanical drive. The case range power shift transmission lets the operator power shift 3 speeds within each mechanical range. Planetary gear sets are used because the gear ratio can be changed without actually engaging the gears, and they triple the number of speed ratios in the 4-speed mechanical drive. When used with hydraulic clutches, the planetary can serve as a direct coupler, a reduction gear, or reversing gear. How this is done is the subject of this program. Planetary gears work like our solar system. The planet gears each turn on their own axis and, at the same time, rotate around the sun gear. This is like the Earth and other planets rotating around the sun. Planetary gears are simple in design, but not always simply understood. To simplify the understanding of the planetary gear design, we're going to build and study the planetary design one gear at a time. We'll start with the input sun gear using a simplified animated drawing. The input sun gear is driven by the engine flywheel through a spring-loaded disc called a torque limiter. The torque limiter protects the drive line from heavy shock loads and vibration. The planet gears are mounted on shafts in the planet carrier and can rotate around their own axis when driven by the input sun gear. This is the long planetary gear and is in constant mesh with the input sun gear. There's also a short planetary gear attached to the planetary carrier. The long and short planetary gears are in constant mesh, so whenever the input sun gear drives the long planetary drives the short one. There are 3 more long and short planetary gears. They all do the same thing, so we'll keep it simple and work with one set. Now let's add another sun gear, the reaction sun gear. The short planet gear is now in constant mesh with the reaction sun gear. So now when we rotate the input sun gear, the long gear, short gear, and reaction sun gear all rotate. This is clutch number 1 in the case power shift system. We'll call it C1 from now on. C1 is attached to the reaction sun gear. If we engage C1 clutch, look what happens. The reaction sun gear stops rotating and the planet gears start rotating around the reaction sun gear. Do you notice something else too? The planetary carrier is also turning. So let's add an output shaft and gear and attach them to the planetary carrier with a clutch. That way we can use the power from the planetary carrier and drive the mechanical 4-speed transmission. But before we do that, let's leave the schematic drawing for a second and take a look at what these parts look like in the power shift. This is the planetary carrier. This is the number 2 clutch, C2, that is attached to the planetary carrier. C2 is connected to an output shaft and gear. The output shaft and gear drive the mechanical 4-speed transmission. Okay, now that we have a better idea of what the parts look like, let's get back to our animated drawing and continue to follow the power path. As we look at this drawing, you are familiar with the input sun gear, planet carrier, planet gears, and the reaction sun gear. Then you'll remember we added the C2 clutch, output shaft, and gear. See those 2 lines connecting the planetary carrier to the C2 clutch? They represent the part of the planetary carrier that houses the C2 clutch. Now, if we start the input sun gear rotating, lock the reaction sun gear up with the C1 clutch, the C2 clutch will turn, along with the planetary carrier. But notice the output shaft and gear? They're not turning, are they? That's because the C2 clutch is not locked to the output shaft. So let's engage the C2 clutch, which locks the carrier to the output shaft. Once C2 is locked to the output shaft, everything turns. A complete power path from input to output. Now, to understand what speed ratio we're in, we'll have to add the ring gear and drum assembly, as well as a third clutch, C3. There are two major driving elements in the power shift that determine the speed ratios. The planetary carrier, which we've already talked about, and the ring gear and drum assembly, which we are going to talk about shortly. When the power shift output is through the planetary carrier, the power shift is in low range, and we have the maximum reduction of the power shift planetary. Before we get into the output of the ring gear and C3, let's go back and review our power path with the planetary carrier as the major driver for low range. C1 clutch is holding the reaction sun gear from turning. This causes the planet gears to walk around the reaction sun gear and the ring gear, causing both the planetary carrier and the ring gear to turn. C2 clutch at the back of the planetary carrier is engaged, locking the carrier to the output shaft and gear. The planetary carrier is driving the output shaft. Thus, it becomes the major drive. The reason the ring gear and drum are not the major drive is because the C3 clutch is not locked to the output shaft. C3 and the drum are just rotating around the shaft. Now let's unlock C2 from the output shaft and lock C3 up. The major power flow is now from the ring gear and drum to the output shaft because C3, which is connected to the drum, is now locked to the output shaft. Notice that the output shaft is turning faster. C1 clutch is still holding the reaction sun gear, only now the planetaries are driving through the ring gear and drum a faster speed ratio, which is intermediate range. The third speed ratio is a direct drive, or high range. High range is achieved by locking both C2 and C3 to the output shaft and releasing the reaction sun gear from C1. With both major drives, C2 and C3, locked to a common output, we have, in effect, created a solid drive out of the power shift planetary. The entire planetary assembly rotates in unison to drive the output shaft. This is high range. Really, the planetary drive power shift is quite simple. Don't you agree now that you've seen how it works? Low range uses the planetary carrier to drive the output shaft. Intermediate uses the ring gear and drum to drive the output shaft. And high range uses the entire planetary rotating in unison to drive the output. Before we conclude our planetary power shift discussion, there are two things more we'd like to show you. One is just what happens when you depress the inching pedal. Well, first of all, pushing down the inching pedal releases all three clutches, C1, 2, and 3, from the parts they normally hold. At the same time, it applies the number 4 clutch, C4, which holds the ring gear and drum stationary. Then look what happens. The planetary gears and carrier turn counterclockwise, but the output shaft does not turn because it is not locked up to either of the major drives by C2 or C3 clutches. Let's just look at that again. You release the 2 applied clutches and apply the C4 clutch, which immediately changes the direction of the planetary drive. Why do we do this? because we want the planetary system to act as a brake. If you just released all of the clutches, there would be enough inertia, or drag, from the clutches traveling close together at high speed to cause the planetary to creep. By applying C4 and reversing the direction of the planetary, it tends to cancel the drag. Everything stops a lot faster, which enables you to shift the mechanical drive a lot easier and faster. Now that you have some idea of what happened when you depress the inching pedal, what happens when you release it? The minute you release the inching pedal, C4 clutch is released. Then C1 and 2 clutches are applied, and you're in low range. Occasionally, we're asked, is it okay to use the inching pedal to downshift? It's up to the customer. Let's look at it this way. The more you use the inching pedal to downshift, the more you are using C1 and C4 clutches. If you use the range lever to downshift, you're spreading out the clutch use among 2 more clutches. That's why we say it's up to the customer. Only they can determine how much the convenience of using the pedal versus the lever is worth. Certainly, there's a lot of convenience and efficiency in being able to use the inching pedal to downshift at the end of the field, especially when you're trying to turn and operate 2 or 3 remote levers at the same time. On the other hand, when you're in the middle of the field and have a free hand, it makes sense to downshift with the lever and spread your clutch life out. Can you see why we say it's up to the customer? While we're still on the subject of the inching pedal, there are some things we don't want the customer to do. One is sitting with the inching pedal depressed for a long period of time, or operating continuously in reverse, like operating the PTO in reverse. The reason is that the bearing life in the planetaries will be definitely shortened because of the phenomenal speed the planetaries are turning at in these 2 applications. The other thing we don't want the customer to do is lug the engine down until it almost kills before they push in the inching pedal. Why? Because at this point the engine has reached peak torque, and when you push in that inching pedal and reverse the planetary, you're putting a tremendous shock load on the torque limiter. If you do this very often, it will shorten the life of the torque limiter. The best way to avoid this is to downshift before the engine lugs down. This is especially true with PTO-operated harvesting equipment. You'll get a better job from your equipment if you downshift and let the crop flow through the equipment. Don't force it through. The one range we've not talked about is reverse. In our inching pedal discussion, you saw how C4 clutch reverses the direction of the planetary. All that is necessary now is to lock the planetary to the output shaft. We do that with the C2 clutch. That's reverse. As you have watched us build up the range power shift, you have to admit it's simple. There are no elaborate disconnect clutches that work in oil or are hydraulically actuated. Just a simple torque limiter to reduce abrupt or lurching speed changes under peak loads. The torque limiter, together with the input sun gear, provide the input to the R.P.S. from the engine. The outputs are simple too. The Planetary Carrier provides the low-range output at about 60% of engine speed. The drum provides another output, intermediate range, at about 80% of engine speed. If you lock all of these elements up together, the R.P.S. works as a solid shaft, and the output is high range because everything turns at engine speed. That's the case range power shift. There is never a compromise on travel speeds because the R.P.S. lets you match engine loads with drawbar loads. It lets you increase your working speed, farm at 5 miles per hour. Lets you control the throughput on PTO machines by controlling the ground speed to the crop input. 3 simple on-the-go power shifts in each of the 4 mechanical ranges permit instant matching of speed and power to challenge soil and field conditions so you can keep moving through tough spots, soft spots, uphill over waterways and headlands to make you more productive.